An algorithm is a hardware-independent specification of a computation. By hardware-independent, I mean that it doesn't specify what the computer should be made of, only the effect that it should have on information that's provided to it as input. So that if you had access to any technology that allowed you to build a computer, a universal computer, you could translate the algorithm into a program for that computer which would perform the information processing that the algorithm specifies. An algorithm is a way of performing a computational task, like sorting a list or factorizing a number. In general, to specify a computational task, you specify properties that the output information should have as a function of the input information. So, a computational task is a problem to which an algorithm is the solution. The algorithm that I'm going to describe today is probably the simplest of all quantum algorithms. So, I'll first describe the problem that it solves. You're given a black box containing a computer that's dedicated to computing a particular function f using reversible classical computation. It operates coherently, though, because part of our task is going to be to use this black box as a component in a quantum computational network. You're not allowed to look inside the box. All you're allowed to do is feed qubits into it at one end and then retrieve them at the other end after a fixed time that's independent of the input. Such a box is known as an oracle. The idea of having an oracle in the specification of a computational task is a trick much beloved by complexity theorists, both classical and quantum, because it can greatly simplify the analysis of algorithms. That's because often looking inside the oracle doesn't help you to perform the task, yet it's quite hard to prove that it doesn't. Why that's so often the case is quite a deep question. It's beyond the scope of these lectures, but I'll explain why it's plausible in this case in a moment. Okay, the oracle in this problem computes a Boolean function f with one Boolean parameter. That is to say, f maps the set containing -1 and 1 to itself. Since the oracle performs a reversible computation, it can't just do this, x to f of x. That wouldn't be reversible. The oracle must have an auxiliary input and output. And when it computes f, what it must really be doing is something like this. X and y goes to x and y f of x. That's a reversible computation. And if you want to use the oracle to compute f of x, then you just have to make sure that y is initialized to the value +1. Now, there are only 4 functions that map a single bit to a single bit. The identity, the NOT operation, or delivering a constant output -1 or 1. Internally, the oracle may be computing something arbitrarily complex, or rather one of two arbitrarily complex things, depending on the input. For instance, it might be doing the traveling salesman problem or some other hard problem for one of two graphs, depending on the input, and then reporting some Boolean property of the answer, such as whether the shortest path has an even or odd number of steps. But however complex the oracle is internally, it will be computing one of these four functions. That's why it's plausible that looking inside the oracle won't in general help. The oracle might contain a complicated network with a large number of qubits doing things in parallel. So it might still be a lot faster to run it twice than to work out what it does once. Anyway, a simple computational task, given the oracle, would be find out what f is. Well, the only way to do that without looking inside is to run the oracle once for each possible input. The resulting four pairs of outputs tabulate f. Is it possible to perform that task using only one run of the oracle? Well, we can prove that it isn't. If you're only allowed to run the oracle once, then whatever else you do, you'll have to pick a particular pair of values for its inputs x and y. And you'll get output values x, which you already knew, and y f of x. Only the second of those two outputs even depends on f, so that can't fully specify what f is, because f can be one of four different functions. And it turns out that that is true in the quantum case too. You can't work out what f is without invoking the oracle twice. So quantum computation doesn't help with that task, which illustrates the general fact that quantum computation doesn't speed up all computational tasks, only some of them. And that's one reason why quantum complexity theory is fundamentally different from classical complexity theory. Anyway, the problem that we are going to solve with a quantum algorithm is not to find out what f is, but to determine a property of f. Specifically, whether f of 1 equals f of minus 1 or not. Or more concisely, the task is to compute the product f of 1, f of minus 1, without looking inside the oracle. Knowing the quantity f of 1, f of minus 1 certainly doesn't tell you everything about f. It just tells you one bit of information about it, which is half the information in the table of f. So the proof I gave that the previous task requires two calls of the oracle doesn't hold for this task. So, is there any way of computing the single Boolean value f of 1, f of minus 1, using only one invocation of the oracle? For the case of classical computation, it's again easy to prove that there is no way, even though it's only one bit of information this time. Because, again, there are only four possible ways of invoking the oracle in a classical computation, and in all four, the first output is again independent of f, and the second depends on only one of the two values, f of 1 or f of minus 1, never both. So f of 1, f of minus 1 can never be deduced from it. Here's a classical network that finds the answer using two instances of the oracle. This is a controlled NOT gate, which we're using in its capacity as an exclusive OR gate. Alternatively, we could find the answer by invoking one instance of the oracle twice, doubling the running time, like this. The input bits both start at 1. They pass through the oracle, making them +1 and f of +1. Then they each go round a loop. The first one passes through a NOT gate that flips it to -1. And the second goes in again as the auxiliary bit. So the final output is f of 1, f of -1. Strictly speaking, this network runs forever. So I'll leave it as an exercise to modify it so that it delivers an output after exactly 2 oracle invocations. What the quantum algorithm does, in short, is that it uses only one instance of the oracle, and it invokes it only once, but it invokes it with a different input in different universes, which means that the oracle performs different computations in different universes, yielding potentially different outputs. And the single qubit that holds those two outputs in different universes combines them in an interference phenomenon. It exclusive ORs them. A bit like this, except that the invocations of the oracle occur in different universes. To describe the quantum algorithm that does that, as with most quantum algorithms, it's simplest to work in the Schrödinger picture, where, as you'll recall, the observables are constant matrices and the state changes with time. In this problem, we can make the further simplification of considering only pure states. Remember that a quantum system is said to be in a pure state when its density matrix takes the form ket psi, bra psi for some ket psi. Psi is then said to be the state vector of the system. And we often refer to the state vector as just the state of such a system. The effect of a quantum gate operating between times t and t+1 on an arbitrary pure state is psi of t+1 equals u psi of t, where U is a constant unitary matrix characteristic of the gate. Like the reversible classical algorithms for performing this task, this algorithm involves 2 qubits, and that's not counting whatever qubits might be inside the oracle. Combining 2 quantum systems in the Schrödinger picture is much the same as doing it in the Heisenberg picture. Any tensor product of observables, one from each system, is an observable of the combined system. And if both systems are in pure states, say ket psi and ket phi, then the combined system is in a pure state too, and its state vector is the tensor product of psi and phi. We write the tensor product of kets without any explicit multiplication symbol like this. And that's a ket of the combined system. Consider a system of 2 qubits then, in an eigenstate of both their z observables, z1 and z2. The four such eigenstates, ket A, ket B, where A and B range over the eigenvalues plus and minus 1, form an orthonormal basis in the four-dimensional vector space of all pure states of the combined system. The space of all pure states that a system could be in is technically a Hilbert space. Basically, that's just a vector space with a norm. And we usually refer to it as the Hilbert space of the given system. Strictly speaking, pure states are always unit vectors. That follows from the definition of a pure state that I've given, because the trace of the density matrix has to be 1. But it's no big deal. Some people like to work with unnormalized vectors, and they insert a normalization factor in this formula. So unnormalized kets are usually called states too, and eigenvectors of observables are called eigenstates. The normalized pure states lie on a unit sphere in the Hilbert space. And all the non-zero states along any straight line through the origin represent the same physical state. When working with pure states, we usually pick a fixed basis in the system's Hilbert space and express the evolving state of the system as a linear combination with time-varying coefficients, time-varying complex coefficients of those basis states. A linear combination of states is called a superposition. In quantum computation, we call whatever basis we choose for doing that the computation basis. We can choose any basis as the computation basis, but usually some choices are more convenient than others. Usually the most convenient one is determined by the classical operations that form part of the computation. I'll explain. In a classical computer, the state of the computation at each step is specified by the sharp values of a set of observables, the computational variables. So when a quantum computer simulates a classical computer, there's a set of observables which are sharp at the beginning and end of every step. And that sharpness is maintained because, as I mentioned last time, the elementary classical operations in a quantum computer have the property that a particular set of observables evolve autonomously. We usually use a notation in which these are the Z observables of the qubits. So that means that during periods when our quantum computer is executing only classical operations, the Z observables of the qubits are distinguished by being the observables on which those gates perform classical operations. Note that in general, the Z observables will not be sharp during those classical operations because they need not have been sharp when the classical part of the computation began. Some earlier quantum operations will in general have made them unsharp. Nevertheless, the Z observables form an autonomous evolving system under classical operations. And that's why the basis of eigenstates of those Z observables is often the most convenient one to use as the computation basis. I'll explain. Classical reversible computations, starting in a computation basis state, proceed from computation basis state to computation basis state. For this and other reasons, the dynamics of simple quantum gates are particularly easy to represent in the Schrödinger picture. It's enough to specify the behavior of each member of a set of basis states, such as the computation basis. For instance, the NOT gate is a single qubit gate. A single qubit has a two-dimensional Hilbert space. So we can completely specify the behavior of the NOT gate by giving its effect on just two states, like this. Ket A goes to ket minus A, where A is plus or minus 1, and these are eigenstates of the qubits Z observable. This statement means that if the state at time 0 is the eigenvalue A eigenstate of Z, then the state at time 1, after the gate has acted, is the eigenvalue minus A eigenstate. Compare that with the description of the NOT gate in the Heisenberg picture, and you begin to see why the Schrödinger picture is preferred for most calculations in the quantum theory of computation. Another important single qubit gate that I haven't mentioned before, and which is used in the algorithm I'm going to describe, is the so-called Hadamard gate, named after the mathematician Jacques Hadamard for historical reasons. It has this effect. Ket 1 goes to 1 over root 2 ket 1 plus ket minus 1, and ket minus 1 goes to 1 over root 2 ket 1 minus ket minus 1. The Hadamard operation is, like the NOT operation, a square root of the unit operation. It's its own inverse. But unlike NOT, it doesn't have a classical analog. By the way, the square root of 2 factor is just there to normalize the states. Now, here's the definition of the controlled NOT gate in the Schrödinger picture. Look how simple it is. It evolves a system of 2 qubits in the eigenstate x, y of the observables Z2 and Z1 into the state x, xy. The ket x, y is just another way of writing the tensor product ket x, ket y. And again, compare this with the Heisenberg picture definition of the controlled NOT gate. The operation of the oracle is as follows. Ket xy goes to ket x, y f of x. Now for the algorithm. Our 2 qubits start in the state where they're both sharp with the value plus 1. We could think of that as the blank state of our 2 qubit computer memory. By the way, when analyzing algorithms in general, the algorithm should always start with a state where all the qubits that are not given as part of the task are blank. That way, your analysis will automatically account for the resources required for any other initialization that you might want to do. The quantum network that solves our problem contains a NOT gate, 3 Hadamard gates, and the oracle. At time 0, the beginning of the computation, the state of each qubit is the eigenvalue plus 1 eigenstate of its Z observable. So the overall state at time 0 is the tensor product of those, which we can write 1, 1. Then the second qubit encounters a NOT gate, which flips its Z observable to -1. Next, both qubits pass through Hadamard gates, and we can just substitute from the definition of the Hadamard gate what the state will be at time 2. 1/2 ket 1 plus ket minus 1 times ket 1 minus ket minus 1. Then the oracle acts on the qubits once, but neither of the Z observables in the input is now sharp. So we're presenting the oracle with 4 different inputs in different universes. Next, well, the oracle will in general take a long time to run, but the running time is a constant independent of the input, and we're not interested in what it is for the moment. So let's just call the time when it's complete time 3. And again, we can fill in what psi of 3 will be. At this point, the computation isn't quite finished yet. We still have that final Hadamard gate to go. But let's just look at this state. Suppose that f of 1 does equal f of minus 1. So we can call them both f. Then the state at time 3 will take this form, which factorizes into a tensor product. So we see that the qubits are still individually in pure states, and the first qubit is in a state proportional to ket 1 plus ket minus 1. Okay, that's if f of 1 equals f of minus 1. If they're unequal, then f of 1 must equal minus f of minus 1, which we can call f again. And again, the qubits are each in a pure state. This time, qubit 1 is in a state proportional to ket 1 minus ket minus 1. If we can distinguish those two states of qubit 1, we shall have determined whether f of 1 and f of minus 1 are the same or different. And that's just what the final Hadamard gate does, because Hadamard acting on 1 over root 2 ket 1 plus ket minus 1 is ket 1, and Hadamard acting on 1 over root 2 ket 1 minus ket minus 1 is ket minus 1. And we can summarize that as, at time 4, the state is proportional to ket f of 1, f of minus 1 times some state of qubit number 2. So the Z observable of qubit 1 now contains information that depends logically on the outcomes of the computations of both f of 1 and f of minus 1. And it's sharp. Although those computations were performed in different universes between times 2 and 3, the interference phenomenon effected by the Hadamard gate between times 3 and 4 combined those values and caused the answer to appear in qubit 1 in all the universes. Z1 is sharp at time 4. The problem solved by this algorithm has come to be known as the Deutsch problem, and the algorithm I've just described is known as the Deutsch algorithm. I should say that that gives me slightly too much credit. The algorithm that I originally proposed was somewhat less elegant and significantly less powerful than this one. I refer you to the worked examples to see in what way it was less powerful. The version I've shown you was published in 1998 by Richard Cleave, Arthur Eckert, Chiara Machiavello, and Mike Mosca. The way this algorithm works is typical of how quantum algorithms work in general, at least typical of those that have been discovered so far. Namely, we start out with the state of the system being an element of the computational basis. That is to say, we prepare the Z observables with particular initial values. And the first thing we do is unsharpen those observables so that they contain many possible values, in our case, all 4 possible values. That unsharpening is a quantum operation. Then we perform a classical reversible computation using coherent quantum components. In our case, that's the computation of F by the oracle. But this computation is being done with different inputs in different universes, giving different outputs too, and then these outputs are somehow combined using another quantum operation, which gives a sharp answer in this case, and more generally, as sharp as possible an answer as the output. And that means that these computations are interference phenomena. Observables which are sharp become unsharp and then sharp again. An algorithm which performs multiple classical computations on unsharp inputs and then combines them is said to be using quantum parallelism. That's because, as I've shown, the process is reminiscent of classical parallel computation, with the difference that you don't need a second copy of the oracle. You use the parallel universe counterparts of the one you're given. Okay, so by using this quantum algorithm, we've gained a factor of 2 in speed. But the real significance of the existence of this algorithm is not its speed, it's the fact of being able to manage with just one evaluation of F to obtain information that depends logically on both values. It's the fact that during that function evaluation, something is going on that cannot be analyzed as a sequence of states in which each computational observable has a single value. This is the characteristic of this new mode of information processing, which is not the implementation of any classical algorithm, and performs a task that no classical algorithm can perform. The ability to perform this particular task is unlikely to have any practical application, though. Well, in some very contrived circumstances it just might. Say you have a time limit by which you have to perform a very important computation that consists of evaluating f of 1, f of minus 1 for some complex algorithm f. As I said, the real significance is theoretical. But next time, I'll describe an amazing quantum algorithm, again using quantum parallelism, that is both theoretically interesting and likely to be useful in a wide range of practical applications.